This video explains how the Find Resonance program works in AreaQuant. What I've done is captured the free induction decay at conditions slightly off of resonance. And you can see that the free induction decay shown here shows several periods indicating that you're a few kilohertz off of resonance. Now the blue and the red curves are the imaginary and real components, and if I click on here I can see the modulus of those values. The modulus is the root mean square of the imaginary and real component at each data point, and one of the things you'll notice is that those are all positive valued. If I take the area under this curve, that corresponds to the integral, or the RMS integral, which when we're doing the Find Resonance program we use to determine how close we are to resonance. So I'm going to turn this off just for a moment, turn these back on, and I'm going to select Find Resonance, and I'm going to start the program. The last saved value of the resonant frequency was 13.507 megahertz. When I run the Find Resonance program, the software is going to apply RF pulses to the receiver coil at increments of 10 kilohertz, starting with 100 kilohertz offset from the original value. So we were originally at 13.507, so the first data point is going to be acquired at 13.407, then the next one at 13.417, and we'll incrementally approach the resonant frequency in 10 kilohertz steps. Let's see what that looks like. So initially we're 100 kilohertz off of resonance, and we see that there's essentially no signal here, that you don't see any waves, and you see these data, which is just an artifact of the measurement. There's essentially no signal there. Now as we progress towards the resonant frequency, we see free induction decay start to appear here. You'll see two things happen as we get closer to resonance. One is the magnitude of the decay will increase, and the second is the period of the oscillations will decrease. Now you see we're at about 54 kilohertz off of resonance, and as we move closer, the peak in the Fourier transform gets closer to the actual resonant frequency, and the number of cycles decreases. So if we take these data and look at the results that you get on screen on the software, the blue curve is the integral of the root mean square values of the FID. The red curve essentially indicates the reciprocal of the number of zero crossings in the FID. So when you're far away from resonance, you have many zero crossings, and as a result the reciprocal is going to be very small. When you get close to the resonant frequency, you should have only one zero crossing, and so the value of this red function will be maximized, and we can use that to pick off the peak value in resonance. In practice, when we're running Find Resonance, we scan through twice, initially at 10 kilohertz, and then we look at the peak in the component integral, and then rescan at in 1 kilohertz increments, in a bandwidth 10 kilohertz around the peak in the red curve. And that's how Find Resonance works.